Welcome to episode 71, Threat Modeling and Secure Design Concepts, where we explore how designing out risk early leads to fewer vulnerabilities later. Threat modeling is the structured act of asking what could go wrong before building, deploying, or changing a system. For HITRUST R2, it proves that the organization understands its environment, anticipates attacker goals, and designs controls to counter them. It also produces living documentation that connects architecture choices to measurable risk reduction. Secure design concepts complement threat modeling by defining universal principles, least privilege, defense in depth, and secure defaults that shape every build decision. Together, they make security proactive rather than reactive. In this episode, we show how to make threat modeling repeatable, evidence-friendly, and practical for teams that must deliver both innovation and assurance.
Designing out risk means preventing weaknesses from entering systems at all, not patching them afterward. Every later control scanning, monitoring, or response exists because of something missed in design. By identifying potential threats early, teams can avoid expensive remediation, reduce audit effort, and build confidence that security is engineered in. This mindset applies equally to software, infrastructure, and business processes. R2 requires not just deployed controls, but proof that security thinking begins upstream. Threat modeling fulfills this requirement by documenting the logic behind architecture decisions, showing how identified risks were mitigated or accepted. The result is efficiency, fewer findings, shorter audit cycles, and systems that are safer by construction rather than recovery.
Threat modeling achieves a specific purpose. It translates complex architecture into a clear understanding of who might attack, what they might target, and how defenses align to those possibilities. It captures adversary goals, such as stealing data or disrupting availability, and maps them to system design. Teams then evaluate each path to determine which threats are credible, how severe the consequences would be, and which controls address them. For example, a payment system might identify tampering threats during transaction processing and counter them through integrity checks and secure logging. The key outcome is clarity. Stakeholders understand which risks matter most and which controls protect the crown jewels. In R2, this structured awareness demonstrates intentional design rather than accidental security. Defining system scope and trust boundaries ensures that modeling focuses on what truly matters. The scope outlines where the system begins and ends, what components, users, and interfaces are included. Trust boundaries mark transitions between different security zones or administrative domains, such as between internal networks and cloud providers. Every crossing represents a potential attack vector that deserves scrutiny. Documenting these boundaries visually in data flow diagrams or architecture maps clarifies which connections require authentication, encryption, or monitoring. Without defined boundaries, threat discussions become theoretical and endless. With them, teams can prioritize defenses at the interfaces where control changes hands. R2 reviewers expect to see this level of clarity, showing that no untrusted pathway remains unanalyzed. Identifying assets, data, and critical paths gives threat modeling its targets. Assets include not just hardware or software, but also business functions, credentials, and information flows. Critical paths are the sequences that, if disrupted, would stop operations or compromise sensitive data. Mapping these elements allows teams to link risks directly to business impact. For example, an electronic health record system's critical path includes patient lookup, update, and billing transmission. Losing availability in that path means delayed care and potential regulatory violations. By linking assets and paths to data classifications, like protected health information, the model stays grounded in operational context. This mapping becomes a reusable reference for other risk activities, unifying how the organization understands its most important resources. Threat libraries and attacker objectives provide the raw material for analysis. Libraries such as STRIDE, OWASP Top 10, or MITRE ATT&CK list known attack types, techniques, and goals that can be adapted to your environment. These references prevent teams from overlooking obvious risks and bring consistency across projects. Attacker objectives contextualize the library. What would a real adversary want from this system? Data theft, disruption, fraud, or lateral movement? Using a shared threat vocabulary allows security and engineering teams to communicate in the same terms.
R2 assessors value standardized frameworks because they show discipline and repeatability rather than improvised reasoning. Threat libraries turn abstract creativity into structured analysis, ensuring that imagination is guided by evidence. Misuse, abuse, and failure scenarios translate technical threats into human stories that resonate with designers. A misuse scenario describes how a system feature could be intentionally exploited, like a self-service portal used to harvest user data through exposed APIs. An abuse scenario considers legitimate users who manipulate processes, such as administrators exporting full datasets without approval. Failure scenarios examine what happens when controls fail accidentally, like logging misconfiguration leading to missing evidence. Writing these scenarios exposes blind spots and helps prioritize fixes before code or deployment. For R2, documenting these examples shows assessors that the team did not stop at high-level theory. They examined real-world behaviors and validated that controls hold up against misuse, abuse, and error alike. Controls mapped to high risks demonstrate that modeling results lead to action. Each significant threat should pair with one or more mitigations, technical, procedural, or contractual, and show who owns implementation. For instance, a data exfiltration risk may map to outbound firewall rules, data loss prevention, and employee awareness training. R2 assessors will look for traceability between identified threats and implemented controls in both design documents and evidence repositories. This linkage transforms threat modeling from an academic exercise into operational proof that risk drives control design. Mapping also prevents redundant safeguards or gaps where a threat remains unaddressed. When every critical risk ties to a visible control, reviewers see a mature, accountable design process. Capturing security requirements early keeps controls aligned with system purpose. These requirements should appear in design documents, user stories, or acceptance criteria, not just afterthought checklists. Examples include encryption mandates, authentication mechanisms, or segregation of duties for administrators. Early inclusion means these controls are built, tested, and budgeted from the start. It also prevents conflicts between performance and security later. For R2, assessors expect to find traceable requirements within design artifacts and project plans showing review and approval. Organizations that treat security requirements as design constraints, like safety or usability, achieve higher assurance with less friction. Security that arrives early fits naturally. Security added late feels forced and incomplete. Design reviews and decision records prove that secure design concepts are applied consistently. A review involves structured evaluation of proposed architectures or changes by security, engineering, and risk representatives. Decision records document outcomes, accepted designs, mitigations, or exceptions with rationale and sign-off. Keeping these records shows auditors how security considerations influenced actual builds. For example, a decision record might show why a particular encryption library was chosen and how alternatives were evaluated. Regular reviews also provide checkpoints for updating threat models as systems evolve. Evidence from these meetings satisfies R2 requirements for governance and continuous improvement, confirming that design security is not one-time validation but an ongoing conversation. Dependency risks and third-party considerations expand modeling beyond internal code and hardware. Most modern systems depend on libraries, APIs, cloud services, or open-source components. Each dependency introduces potential vulnerabilities or changes the trust boundary. Governance must include periodic validation of third-party updates, vulnerability scanning, and license compliance checks. For example, when an open-source library handles authentication, the model should consider how quickly patches are applied if a flaw appears. Documenting these dependencies and associated risks assures assessors that supplier security is not assumed but actively managed. This layer of analysis connects threat modeling with vendor risk management, reinforcing R2's broader assurance framework. Iteration with changes and learnings keeps threat modeling alive throughout a system's lifecycle. Architecture evolves, and so must the model. Each major release, new integration, or incident post-mortem should trigger review and update of threats and mitigations. Maintaining version history and changelogs shows that the model reflects reality, not history. For instance, when new encryption standards or deployment patterns emerge, those changes update both risk analysis and control design.
Continuous iteration proves maturity because it integrates lessons learned into future builds rather than treating them as isolated fixes. For R2, an outdated threat model is almost as risky as none at all. Currency equals credibility. Evidence artifacts acceptable for assessors demonstrate that modeling outputs are documented and reviewable. Typical artifacts include system data flow diagrams, threat catalogs with severity rankings, mitigation maps, and approved design decision logs. Meeting notes, review sign-offs, and update records also count. Each artifact should show author, date, and version, proving traceability. Tools like Microsoft Threat Modeling or equivalent frameworks can export structured reports, but even spreadsheets or wikis qualify if they capture detail consistently. Assessors will sample these artifacts to verify that they align with implemented controls. Clarity, completeness, and accessibility matter more than formatting. The evidence must show that thinking occurred, actions followed, and oversight continued. Common pitfalls in threat modeling include excessive complexity, outdated diagrams, or narrow focus on only technical threats. Simplification tactics help sustain momentum. Use standard templates, focus on top impact scenarios, and integrate modeling into existing design reviews instead of making it a separate bureaucracy. Encourage collaboration between developers, security engineers, and risk analysts so analysis remains practical. Avoid trying to model every possibility. Instead, ensure the most relevant ones are addressed thoroughly. For R2, simplicity that works beats sophistication that stalls. A concise, current, and actionable model is more defensible than a thick document no one maintains.